Alright, today we're going to look at a tutorial on how to calculate the sampling distribution of a sample mean. There's going to be a couple parts to this tutorial today. First we'll look at the question. We're going to do a little bit of review on the central limit theorem. We're going to need that for calculating the sampling distribution. And then we're going to actually calculate the sampling distribution for a few different sizes. Sample sizes, that is. Alright, so here's the question. So a study in the Journal of Real Estate and Economics showed that loan amounts of loans originated by a large insurance company. They had a right-skewed distribution with a mean mu equals $6.74 million, and then a standard deviation of sigma equals $15.37 million. So that right-skewed distribution tells us that they have tons of loans down in the lower range, down in the millions, and it looks like they do have some pretty big loans, you know, tens, hundreds of millions maybe, but not too many of them, right? So right-skewed, that means getting dragged up towards the right skew. Of course, the median would be a little lower. So here's the idea. Suppose you're going to take a random sample of N loans. And these are the ones originated by the insurance company. So you're going to go and you're going to randomly select a bunch of the loans they're holding. So using millions of dollars, what I'd like you to do is determine the sampling distribution of X bar, which would be the average value of the sampled loans. And let's do it for a few different sample sizes. So the first sample size we're going to look at is maybe N equals 25, then maybe N equals 100, and N equals 600 finally. So let's look back at the central limit theorem for a minute. You're going to want to recall that if you take a random sample of size n from a population with mean mu and standard deviation sigma, as long as you have a relatively large sample size, we know that the variable x bar, the sample mean, it should be approximately normally distributed, and it'll have the parameters with a mean centered around the true population mean, that's mu, and then the standard deviation should be the population standard deviation divided by the square root of the sample size. Now, the question is, how large is large enough for n? Well, it kind of depends. If you have at least 30 sample sizes, then you should be good to go. Now, if your population happens to already have a normal distribution, then you can actually get away with a lot smaller sample size. If your population happens to be highly skewed, then you may actually need more. This is a good example of why it's a good idea to graph your data before you start doing inference to see whether you think it's relatively normally distributed, possibly skewed, possibly highly skewed. In this case, it just said it was a skewed distribution. We don't have a graph. So I think we should just assume it's skewed, but maybe could be highly skewed, we don't know. Alright, so let's move on to the actual calculating sampling distributions. Now in part 1, suggested calculating the sampling distribution for x bar when n is equal to 25. So you're going to go sample 25. Now, here's the problem. The population was identified as skewed. We can't use the central limit theorem for sample sizes less than 30, especially with a skewed population. So in this case, the sampling distribution of the sample mean is really unknown. We don't know if it'll be normally distributed. We're not totally sure what it's going to look like. So we shouldn't make any sort of inferences, and we shouldn't assume that it's going to be normally distributed. Now, in part 2, when you increase your sample size up to 100 though, this is a totally legitimate sample size. It's definitely bigger than 30. I think we can use the central limit theorem, even if our population is pretty skewed. 100 samples is definitely enough to start to see normality in the sample mean. So we know the distribution will be approximately normal. Now we just have to calculate the mean and standard deviation. So the mean of the sampling distribution will be centered around the true mean. That's $6.74 million. That comes from the information in the prompt of the problem. To calculate the standard deviation, we just need to take the population standard deviation divided by the square root of the sample size. In that case, the population standard deviation was 15.37 million. We're going to divide it by the square root of the sample size, where the sample size was 100. If you take that calculation, 15.37 divided by root 100, you should get $1.537 million. So, to wrap it up, the sampling distribution of x bar, the sample mean, that'll be approximately normally distributed. It'll have a mean of $6.74 million and a standard deviation of $1.537 million. Alright, so in the last part, we just want to increase our sample size. So suppose we take an even bigger sample size, 600. Well, in this case, the sample size is still definitely large enough, right? Definitely more than 30, and even more than 100. So we're still going to be able to use the results of the central limit theorem. We know it's going to be normally distributed, but we have to calculate that mean and standard deviation again. Now, the nice thing about the central limit theorem, it tells us that it's still going to be centered around the population mean. It's because x bar is an unbiased estimator of mu. So it'll still be centered around the true mean, which is $6.74 million. The standard deviation, we'll calculate it just like last time, except for now our sample size has increased to 600. So we'll have to take 15.37, which is the population standard deviation, and divide by the square root of 600, our new sample size. If you make that calculation, you should get about 0.8874, and remember, this is in millions of dollars. And notice, your sample standard deviation has gone down since your sample size went up. This is always the case. As you take more and more samples, your sample standard deviation always goes down. And it makes sense because as you take more samples, you would expect that your mean should be getting closer and closer to the true mean. Alright, so to wrap it up, our final answer here is that the sampling distribution of x bar will be approximately normally distributed with a mean of mu x bar equals $6.74 million and a standard deviation 0.8874 million.